We start our microscopic description of current by looking at a conductor with a set number of charge carriers per unit volume. If we take this number and multiply it by the size of a volume with cross-sectional area A and length x, and multiply this number again with the amount of charge each carrier has, we end up with the total amount of charge in the volume shown on the screen. If we assume a current is flowing in the conductor, the current has to be proportional to the rate at which charges leave the volume shown on the screen, or alternatively, the rate at which charges flow across the cross-sectional area A. If we assume that the charges are uniformly distributed through the volume, it means the current therefore is proportional to the time derivative shown on the screen, where we have now defined the current in terms of a speed, which we will call the drift speed, and which we will soon find out is constant. However, we need to look into how such a drift speed is produced. In order to answer this question, we look at the motion of charges in two different cases. One, where we look at charges in a conductor where the electric field is zero, and the second case where we look at the motion of charges in a conductor in a non-zero electric field. In zero electric field, the charge carriers in a conductor suffer thermal motion or is scattered due to thermal effects, and this results in an average zero displacement and zero average velocity for charge carriers in the conductor. In a non-zero electric field, charges scatter but are also under the influence of the electric force due to the electric field in the conductor. Therefore, the electric field, or application of electric field in the conductor does not produce pure acceleration, but the motion that results is a combination of acceleration in the field direction and scattering inside the conductor, trying to randomize the motion of charge carriers. We can look at this motion more precisely for a class of very special conductors called ohmic conductors. Ohm's law relates the current density, defined as the amount of current per unit cross-sectional area in a conductor, to the electric field inside the conductor through a simple linear relationship, where the constant of proportionality is just called the conductivity of the material. If we take our two expressions for the current density and we solve for the drift speed, we find that for a set electric field in a conductor, the value of the drift speed is constant. And if the conductivity does not depend on the electric field, as Ohm's law implies, again we get that the drift speed is constant. Therefore, in ohmic conductors, we find that the scattering motion of charge carriers exactly opposes the acceleration that would occur due to the non-zero electric field. We can use our previously derived expressions for the potential difference in a conductor to derive a more familiar form of Ohm's law, relating the potential difference across two ends in a conductor to its resistance and the current. The resistance depends on the length of the conductor, its cross-sectional area, and the conductivity of the material itself. We can define a material-independent property called the resistivity, which is the inverse of conductivity, which does not depend on the geometry of it. Where does Ohm's law come from? We can describe Ohm's law by making two simple assumptions. The first is that as charge carriers move in a conductor and they suffer collisions, charge carriers move in straight lines between collisions. Therefore, if I've got a charge carrier and it suffers a collision, it is scattered, and in between, the charge carrier moves in a straight line. Importantly, however, we assume that the motion of the charge carrier after the collision does not depend in any way on its motion before the collision. This implies that any velocity after the collision is equally probable. So all possible velocities that may occur after a collision are equally probable. This in turn implies that the collisions are not necessarily elastic and that some energy will be transferred to the medium with which the charge carriers are colliding. If we make this assumption, the result of charge carriers suffering collisions is that the internal energy of the conductor increases, which in turn means that the conductor heats up. We can model this by using our equations of motion derived for the case of constant acceleration. If v final is the velocity of a charge carrier after a collision, it obeys the equation of motion shown on the screen, where the acceleration is now produced due to the electric field inside the conductor. However, because after a collision all velocities are equally probable, the average velocity for any charge carrier after a collision is 0. If we say that on average a charge carrier suffers a collision every tau seconds, we find that the average speed of a charge carrier, which is equal to its drift speed, is expressible in terms of the electric field in the conductor, the time between collisions, the charge of the charge carrier, and its mass. Knowing the drift speed in terms of the current density now allows us to write down an expression that gives the conductivity of a material in terms of the collision rate or the time between collisions in that particular material. This shows that in materials where there is on average a longer time between collisions amongst charge carriers, we expect a larger conductivity. If there is a short time between collisions, tau is smaller and we expect a smaller conductivity.